NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve a general logarithmic equation using a precise algorithm. Consider the equation. Log base f of g equals log base f of h. We will rewrite it as an equivalent system step by step, exactly following the stated rule. First, write the given equation. I will read it as log base f of g of x equals log base f of h of x. This is our starting point. According to the rule, this single equation is equivalent to the following system. The base must be positive and not equal to 1. The argument on the left must be positive, and the two arguments must be equal. Write that system now. Because the last line states g of x equals h of x, it is sufficient to require positivity for only one of the arguments. That gives a second, but completely equivalent system. In this lesson, we will solve the logarithmic equation. Log base x squared minus 1 of x cubed plus 6 equals log base x squared minus 1 of 4x squared minus x. We'll move carefully. First, build the domain. So the logarithms are defined, then equate the arguments, factor the cubic, and finally check solutions against the domain. Step 1 is domain. For a logarithm log base b of, we need two things. The base b must be positive and not equal to 1, and the argument a must be positive. Here the base is x squared minus 1. So we require x squared minus 1 greater than 0 and x squared minus 1 not equal to 1. Also, both arguments x cubed plus 6 and 4x squared minus x must be positive. Let's visualize the intersection. From the base condition, x is less than -1 or greater than 1, excluding plus or minus square root of 2. From argument positivity, we also need x cubed plus 6 positive, which trims the far left to be greater than about -1.817, and 4x squared minus x positive, which already holds on both allowed wings. So our candidate set is from -1.817 to -1, and from 1 to infinity, with the points plus or minus square root of 2 removed. With the domain satisfied, equal logarithms with the same base imply equal arguments. So we set x cubed plus 6 equal to 4x squared minus x and solve. Bring everything to one side to form a cubic equation equal to 0. Now factor by grouping. Group the first 3 terms and the last 3 terms to create a common quadratic factor. Factor out x from the first group and 1 from the second group to reveal the common factor x squared minus 5x plus 6. Factor out the common quadratic. Finally, factor the quadratic into linear factors. The candidates are x equals -1, 2, and 3. We must check each against the domain. For x equals -1, the base becomes 0, which is not allowed. So -1 is rejected. The values x equals 2 and x equals 3 both satisfy the domain and the original equation. Therefore, the solution set is 2 and 3. Here is our equation. Log base x plus 4 of x squared minus 1 equals log base x plus 4 of 5 minus x. Step 1. Write the equivalent system that enforces the logarithm rules. The argument of each logarithm must be positive, the base must be positive, and the base cannot be 1. So we write the system. 5 minus x is greater than 0. X plus 4 is greater than 0. X plus 4 is not equal to 1. And because the bases are identical, the arguments must be equal x squared minus 1 equals 5 minus x. Step 2, copy the core equality of the arguments. Then move all terms to the left to form a standard quadratic equals 0. Step 3, factor the quadratic. We need two numbers that multiply to -6 and add to 1, that is plus 3 and minus 2. Step 4, apply the zero product rule to get the candidates. So x equals -3 or x equals 2. Step 5, check the candidates with the domain conditions from step 1. Let's build an intuitive number line to test them quickly. The base conditions are x plus 4 greater than 0 and x plus 4 not equal to 1. That means x is greater than -4, but x cannot be -3. The argument conditions are 5 minus x greater than 0, so x is less than 5, and x squared minus 1 greater than 0, meaning x is less than -1 or x is greater than 1. We'll shade the allowed regions. Then we will test the two candidates. First candidate, x equals -3. The base becomes x plus 4 equals 1, which is not allowed for a logarithm. So x equals -3 is rejected. Second candidate, x equals 2. All conditions are satisfied, and both arguments are positive, so x equals 2 is valid. Therefore, the solution set contains only the value 2. We write capital D equals the set containing only the value 2. We write capital D equals the set containing 2. Step 1. Write the original equation exactly as given. Step 2. Use the identity 1 equals log base any base of the base itself. So replace 1 by log base x of x. Step 3. Apply the product rule for logarithms. Log base b of a plus log base b of b equals log base b of a times b. Combine the right side. Step 4. Because the bases are the same and logs are equal, equate the arguments and list the domain conditions shown in the solution image. Step 5. Solve the quadratic that comes from setting x plus 2 equal to 4x minus x squared. Move all terms to one side. Factor. Read the potential solutions. Step 6. Enforce the domain conditions. We must have x greater than 0 and x not equal to 1. Therefore, discard x equals 1. The final solution set is the single value 2. Recap. We replace the 1. The final solution set is the single value 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.